In this lesson, we are going to discuss the chain rule. And the chain rule is a rule that you use when you're trying to take the derivative of a composite function. And a composite function is a function that is made up of one function being plugged into another function. So if our composite function is h of x that we're trying to find the derivative of, then it can be written as f of g of x if it's a composite function. F is the outer function and g is the inner function. And so when you take the derivative of a composite function, what you're going to do is you're going to take the derivative of the outer function evaluated at g of x. So that g of x is going to remain plugged in, and you're going to take the derivative of f as usual, but then you have to multiply by the derivative of the inner function. So you're going to multiply by the derivative of g of x. Now, if you're using the dy dx notation, if you take the derivative of y with respect to x and it's a composite function, think about u as being the inner function. You're going to take the derivative of dy with respect to u and then multiply it by du with respect to x. Okay, so let's go through our first example here. So I want to identify the inner and the outer functions first. So here's my inner function. And I'm using the same notation that's in the theorem so we can be consistent and follow the steps. And then my outer function would be f of x is equal to x to the fourth. So h of x is the composite function f of g of x. So I would take g of x and plug it into f of x. Now, when I take the derivative using the chain rule, I got to find the derivative of f. You still evaluated a g of x, so that inner function is going to remain inside there. And then I'm going to multiply it by the derivative of the inner function. So the derivative of f is 4x to the third. And then if I plug in g of x, that's going to be 4 times 2x to the third plus 2x minus 1. And then that's all raised to the third power. So now I need to find the derivative of g of x, which is 6x squared plus 2. Okay, so now I'm going to put all this in there. So f prime of g of x is 4, and then inside parentheses 2x to the third plus 2x minus 1 raised to the third because I decreased it by 1. And so f of x is still evaluated at g of x. That function is still plugged in there. And then I have to multiply it by the inner function, which would be 6x squared plus 2. Okay, the next example, let's actually apply this to finding the tangent line. So we're still going to go through the same process we have before in the past with finding the derivative, evaluating it at that point to find the slope, and then going through that process. But now when we take the derivative, this is the case where we have a composite function. So I have, if I rewrite h of x as, in parentheses, 3x minus 5 raised to the power of negative 2. That way we don't have to worry about the fraction and using the quotient rule. Now I can identify my inner and outer function. So my g of x, my inner function, is going to be 3x minus 5. my f of x, or my outer function, is going to be x to the negative 2. So to find the derivative of h of x, I need to use the chain rule because I've got a composite function here. So I want to take the derivative of f, which is negative 2, and then I'm going to raise that to the power of negative 3 because I decrease it by 1, but I'm going to evaluate it at 3x minus 5. So that 3x minus 5 needs to stay in there. And then I'm going to multiply it by the derivative of 3x minus 5, which is just 3. So I can clean this up a little bit, and I can bring the 3 in front and write this as negative 6 times 3x minus 5 raised to the negative 3. So now I have the derivative of h of x, and so I can find the slope of the tangent line by evaluating it at 2. So I'm going to plug in 2. When I plug 2 into the derivative, I'm going to get negative 6. So this is the slope of the tangent line at x equals 2. Okay, so we found our slope. So I'm going to plug that negative 6 in for m. Now I got to plug in a point for x and y so that I can figure out what my value of b is. Since I'm looking at the point on the curve x equals 2, I'm going to use 2 for my x. And if I plug 2 back into h of x to find my corresponding y value, I'm going to get 1. So when I solve this for b, I have a negative 12 when I take negative 6 times 2, and then I'm going to add 12 to both sides, so I'm going to get b is 13. So my tangent line is going to be y equals negative 6x plus 13. So you can see that we did the same routine where we took the derivative and found the line. However, when you're taking the derivative, you need to identify what rule to use. And now that we have the composite or the chain rule for composite functions, we can use that as well and add that to our toolbox. Okay, so here's another example of how you can use the chain rule with the power rule. So I'm going to rewrite this function h of x as 3x squared plus 1 raised to the power of negative 2. So my inner function, g of x, is going to be 3x squared plus 1. My f of x, or my outer function, is going to be x to the negative 2. So when I take the derivative of f, I'm going to get negative 2x to the negative 3. And then when I evaluate it at g of x, all it does is it just says we're keeping that inner function in there. And now the derivative of g of x is going to be 6x. Because I bring that 2 down in front and I have 6x. And then the plus 1 is a constant. So when I take the derivative of that term, we get 0. So now to find the derivative of h of x, I take the derivative of my outer function evaluated at my inner function times the derivative of my outer function. So when I put all that together, I'm going to get negative 2, 3x squared plus 1 raised to the negative 3, and that's all times 6x. Now, I can clean this up a little bit by multiplying the negative 2 and the 6x. That gives me negative 12x. And because the 3x squared plus 1 is raised to the negative 3 power, I can bring that back downstairs if I want to leave my exponents as positive. Using the chain rule and the power rules with a trig function. So if you recall, sine cubed x is the same thing as writing this. These two statements are equivalent. So I'm going to rewrite h of x as sine x to the third. So now I can identify what my inner and outer functions are. So my inner function is sine x, and if I take the derivative of my inner function, that's going to be cosine x. My outer function is x to the third, and when I take the derivative, I get 3x squared. But when I evaluate the derivative of f of g of x, it's basically just taking the derivative with that inner function still plugged in. So now if I put this all together, if I take the derivative of h prime x, that is the derivative of the outer function evaluated at g of x times the derivative of my inner function. So the derivative of my outer function evaluated at g of x, we said was 3 times sine x and then squared. And then I multiply that by the derivative of my inner function, which is cosine x. Here's another example of finding the derivative of a composite function that involves trig functions. So my inner function, my g of x, is going to be 5x squared. And when I take the derivative of that, I get 10x. My outer function is cosine x. And when I take the derivative of that, evaluated at g of x, I'm going to get negative sine, and then I keep that 5x squared in there. Okay, so now when I want to find the derivative of h of x, which is my composite function, I'm going to take the derivative of my outer function evaluated at g of x times the derivative of my inner function. So that gives me negative sine of 5x squared times 10x. And we can clean this up a little bit by taking the 10x in front. And we can write it as negative 10x times sine of 5x squared. So here's another example of where you can use the chain rule with a trig function. Here we have that h of x is the secant of 4x to the 5th plus 2x. So we have a composite function here. So the inner function, g of x, is going to be 4x to the 5th plus 2x. The outer function, we'll call that f of x, that's going to be secant x. And so we need to find the derivative of the inner function, which is 20x plus 2. And the derivative of secant is secant x tan x. But then when I evaluate it at g of x, what we get is secant times 4x to the 5th plus 2x times tangent of 4x to the 5th plus 2x, because everywhere I see x, I need to plug in g of x. Now, to actually take the derivative of h of x, we want to evaluate the derivative of f, g of x, and then multiply it by the derivative of g of x. We've already figured out the pieces, we just need to put it together. So f prime of g of x would be secant of 4x to the 5th plus 2x times tangent of 4x to the 5th plus 2x. Now all of this in parentheses is just the f prime g of x. But then when we multiply by the derivative of g of x, we multiply that by 20x plus 2. In this example, we're going to be combining the chain rule and the product rule. So this could get a little messy, so you want to make sure that you take your time and write all your steps. So when we take the product rule, we're going to have two functions. So I'm going to call this f, and I'll call this g. So I have f of x, which is 2x plus 1 raised to the 5th. Then I have g of x, which is 3x minus 2 raised to the 7th. Now, if you notice, f of x and g of x are also composite functions. So this is why we're using the product rule and the chain rule, because we got the product of f times g, but each of those f and g functions are also composite functions. So f is the composite function where you have the inner function 2x plus 1 and the outer function x to the 5th. And g of x has the inner function 3x minus 2 with an outer function of x to the 7th. So when I take the derivative of f, I have to use the chain rule. So I'm going to take the 5 down in front, and I want to keep it evaluated at g of x. And then this is raised to the 4th, because I decreased that 5 by 1. And then I have to multiply it by the derivative of the inner function. So that would be 2. So when I clean this up, I get 10 times 2x plus 1 raised to the 4th. Okay, now let's look at g of x. When I take the derivative of g of x, I got to use the chain rule, so I'm going to bring the 7 down in front. I keep it evaluated at that inner function, which is 3x minus 2. And then I bring the exponent down by 1, so that's 6. And then I have to multiply it by the derivative of the inner function, which is 3. And so when I clean this up, I get that the derivative of g is 21 times 3x minus 2 raised to the 6th. So now, going back to finding the derivative of h of x, we have to take the derivative of f times g plus the derivative of g times f. Now we already found the derivative of each of those separately using the chain rule, so now I can just plug in the values and try to simplify. So we said f prime was 10 times 2x plus 1 raised to the 4th, and we're going to multiply that by g, which is 3x minus 2 raised to the 7th. And then we're going to add that to the derivative of g, which is 21 times 3x minus 2 raised to the 6th, but we have to multiply that by f still, so that's going to be times 2x plus 1 to the 5th. Now, we can clean this up by factoring. I really don't want to actually multiply all of that out and combine like terms, because who really wants to multiply out 2x plus 1 to the 4th and 3x minus 2 to the 7th and clean that up and still have to do the second term as well. So I'm going to do this by factoring. So if you notice, in both terms, here's a term, and then I have addition, and then here's a term. And both of those terms, I have 2x plus 1. One is to the 4th and one is to the 5th. So at most, I can pull out a 2x plus 1 to the 4th. So when I pull out 2x plus 1 to the 4th, what's left over is 10 times 3x minus 2 to the 7th plus 21 times 3x minus 2. And then I still have 2x plus 1 left because I pulled out 4 and there were 5. Now if I look, I still have a 3x minus 2 to the 7th. Whoops, I forgot to carry down that 3x minus 2 to the 6th. And here I have a 3x minus 2 to the 6th. So at most I can pull out a 3x minus 2 to the 6th. So on the outside now I have 2x plus 1 to the 4th times 3x minus 2 to the 6th. And on the inside I'm left with 10 times 3x minus 2 to the 1st, because I pulled out 6 of them, plus 21 times 2x plus 7. Now, this is a lot easier to distribute and clean up. So I have 2x plus 1 raised to the 4th times 3x minus 2 raised to the 6th. And when I distribute and combine like terms on the inside of those brackets, I'm going to get 72x plus 1. Now here's an example of where we would use a chain rule with the quotient rule. So I have a function on top, I'll call that f. And a function on the bottom, I'll call that g. So f of x is x. So the derivative of x is just 1. G of x is the composite function 2x plus 3 to the 3rd. And I know that that's a composite function because my inner function would be 2x plus 3. My outer function would be x to the 3rd. So when I take the derivative of g of x, I have to use the chain rule. I bring the 3 down in front. I keep it evaluated at that inner function. I decrease my power by 1, so that's 2, times the derivative of the inner function, which is 2. And when I clean that up and I bring the 2 in front and multiply it by the 3, I get 6 times 2x plus 3 raised to the 2nd power. That's my derivative of g. All right, so now when we go to evaluate h of x, for the quotient rule, we have the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom function squared. So in the numerator, I have the derivative of f, which we said is 1, times g, which is 2x plus 3 to the 3rd, minus, now I have the derivative of g, which we said was 6 times 2x plus 3 to the 2nd power, times f, which is just x, all over the denominator function squared. So this is going to be 2x plus 3 and it's cubed, but when I square it, that becomes 6, because when you raise a power to a power, you have to multiply. So the 3 now becomes a 6 when I square it. Now I can take out a 2x plus 3 squared in all of these terms when I clean this up. So if I take a 2x plus 3 squared out of the first term, I'm left with just 2x plus 3. When I take a 2x plus 3 squared out of that second term, I'm just left with minus 6x. And when I take a 2x plus 3 squared out of the denominator, that gives me a 2x plus 3 to the 4th. Then on the top, I can clean it up a little bit more and write 2x plus 3 minus 6x as minus 4x plus 3 all over 2x plus 3 to the 4th. In this next example, I'm going to show you a function that you have to use the chain rule more than once. So this is a composite of 3 functions. And let me show you, when I rewrite this, what that looks like. Don't forget that cosine written like this, cosine to the 4th x, is the same thing as saying cosine x to the 4th. These are equivalent. So I'm going to rewrite cosine to the 4th of 7x squared plus 1 like this. So we have the inner function 7x squared plus 1. That's the inner function for the cosine. Then we have another inner function, which is the cosine of 7x squared plus 1. And then the outermost function is x to the 4th. So we have multiple functions here. So when we take the derivative of something like this, you're literally just going to use the chain rule more than once. So you're going to bring the 4 down in front, and you're going to keep it evaluated at cosine of 7x squared plus 1. And you bring, the exponent is decreased by 1. So when I take the derivative of that inner function, it's going to be negative sine of 7x squared plus 1. But then the derivative also has an inner function, so I have to take the derivative one more time of the innermost function, which would be 14x. So I use the chain rule more than once here because we have a composite function that's made up of 3 functions. So I have the outer function, then I have like the middle function, it's an inner function, and then I have the innermost function, which is the 7x squared plus 1. So we can clean this up a little bit. If we take 14x times 4 and we bring that in front, we would get, what's that, 56x. And I can bring that negative that's in front of the sign in front as well. So that would give me negative 56x. And then I have cosine of 7x squared plus 1 raised to the 3rd times sine of 7x squared plus 1. Okay, here's an example of using the chain rule with a velocity problem. So again, it's the same problem we've been doing, but now we're just going to do an example of when we take the derivative with the chain rule. So it says a particle moves along the coordinate axis. Its position at time t is given by the function, which is a position function. S of t is usually a position function. So we have sine of 2t plus cosine of 3t. What is the velocity of the particle at time t is equal to pi over 6? So if we want to find the velocity, we need to take the derivative of the position function. And if you notice, the sine has an inner function, which is 2t, and we have cosine, which has an inner function of 3t. So when we take the derivative, we have to remember to use the chain rule. So I have s prime of t is equal to the velocity, which is going to be the derivative of sine 2t, which would be cosine 2t, but then I have to multiply it by the derivative of the inside function, which is 2. And then I'm going to add that to the derivative of cosine 3t. The derivative of cosine is negative sine. So I keep that evaluated at the inner function, and then I multiply it by the derivative of the inner function, which is 3. So when I clean this up, I'm going to get 2 cosine of 2t minus 3 sine 3t. So there's my velocity function when I take the derivative of the position. Now I want to plug in pi over 6 to find the velocity, keeping in mind that the t represents time, even though it doesn't specifically say what the units are. T represents hours, seconds, minutes, or something like that. So the velocity is going to be some kind of distance divided by time unit. So when we plug in pi over 6, we get the cosine of pi over 3 minus 3 times sine of pi over 2. And then, whoops, I don't need that. Cosine of pi over 3 is 1/2. Sine of pi over 2 is 1. So I have negative 3 times 1, which is negative 3. So my velocity is going to be negative 2. And that negative just tells me it has switched direction from the initial direction. Okay, next example, we're going to take the derivative using the chain rule, but rather than actually get the formula of the function, we're going to just use the point values that are given to us. So it says let h of x be the composition function f of g of x. So g is the inner function, f is the outer function. So when I take the derivative of h prime, I'm going to take the derivative of f evaluated at g of x, and then I'm going to multiply it by the derivative of g of x. The question asks us to evaluate the derivative at 1. So now I'm going to plug in 1 everywhere. So g of 1 is given to us up here. It says g of 1 is 4. So I'm going to plug in g of 1 is 4. It says g prime of 1 is 3. And then it also tells us that f prime of 4 is 7. So I'm going to get 7 times 3, which gives... So the last topic that I want to cover with you in this lesson is we're still going to talk about the chain rule, but we're going to do it in terms of the Leibniz notation, which is the Dydx notation. And so when you're dealing with the chain rule and you're using the Leibniz notation and you take the derivative of y with respect to x, that's going to be the derivative of y with respect to u. So I want you to think of u as that inner function times the derivative of u with respect to x. So we're going to identify u as the inner function, which is x over 3x plus 2. Now, when I take the derivative of u with respect to x, and I say with respect to x because my independent variable is x, we're going to use the quotient rule. And because in this example, I want to focus more on the notation rather than the actual quotient rule, I'm just going to tell you what you get when you take the derivative of u. You're going to get 2 over 3x plus 2 squared. So that's using the quotient rule. That's your du dx. Now, if I identify my y, which is my outer function, that's going to be u to the fifth. So when I take the derivative of y with respect to u, now I take the derivative of y with respect to u here because u in this case is my variable. I'm going to bring the 5 down in front and I have u to the fourth. So now, going back to the definition here, it says to find the derivative of y now with respect to x. So I want my derivative to be all in terms of x. I take the derivative of y with respect to u and multiply it by the derivative of u with respect to x. So that's going to give me, when I take dy du, dy du we said was 5u to the fourth. And I'm going to multiply that by du dx, which is 2 over 3x plus 2 squared. Now, the last step is to resubstitute and simplify if you can. So I'm going to plug in our value of u in here, which we said was x over 3x plus 2. And that's raised to the fourth times 2 over 3x plus 2 squared. So when I clean this up, if I multiply across the top, I have a 5 times an x to the fourth times a 2. That gives me 10x to the fourth. When I multiply across the bottom, I have 3x plus 2 raised to the fourth times 3x plus 2 raised to the second. So that's going to give me 3x plus 2 raised to the sixth. So let's use the Leibniz notation again one last time to practice on a tangent function. So we're going to identify the inner function as 4x squared minus 3x plus 1. And our outer function, which is our y, tangent u. Okay, so now when I take the derivative of u with respect to x, because x is our variable in this equation for u, I'm going to get 8x minus 3. When I take the derivative of y with respect to u, remember the derivative for tangent u is secant squared u. And so now when I use my notation, if I want to find the derivative of y with respect to x, I'm going to find the derivative of y with respect to u times the derivative of u with respect to x, which in this case gives us secant squared u times 8x minus 3. And then when I go back and substitute back for u, I get secant squared, and u was 4x squared minus 3x plus 1. And then that's all times 8x